Hello everybody, welcome back to another Gaussian math video. In this video, I'm going to be doing 5 exercises about units and Gaussian integers, and I think I'm going to start doing this in all of my series because it's an extra, 5 theorems or, things, and it's 5 theorems or lemmas or whatever, and why not? So, yeah, sure, I'll start doing this. I have the exercises here. Don't think I'm doxing myself. Alright, so the first one is, show that a Gaussian integer alpha is a unit if and only if its norm is 1. So the reason for this is, alright, so we'll show it this way first. So alpha is a unit, so if alpha is a unit, there exists a Gaussian integer beta such that alpha beta equals 1. Therefore, the norm of alpha times the norm of beta equals the norm of 1 equals 1. Therefore, the norm of alpha equals the norm of beta, which equals 1. Alright, and now the other way. So its norm is 1 implies it's a unit. Well, if the norm of alpha equals 1, that means that a squared plus b squared equals 1, where alpha equals a plus bi. And therefore, a squared equals 1, and b squared equals 0. Or b squared equals 1, a squared equals 0, which means that alpha must be in the set containing plus or minus 1 or plus or minus I. Because when b is squared equals 1, then b is plus or minus 1, and when a is 1, a is plus or minus 1. Alright, so that's the first one done. Let's do the second one. Oh crap, I've already... Okay. Alright. Let's do the second one then. The second one is show that in the ring, so given an alpha and beta in the Gaussian integers, show that alpha beta equals epsilon gamma to the n for alpha and beta relatively prime, so they're greatest common divisor is 1, and epsilon a unit. I'll just say alpha and beta relatively prime, because I think it means that up to a unit, so I can't say that actually. And epsilon a unit implies alpha equals epsilon prime times some zeta to the n, and beta equals epsilon double prime or however you pronounce it to the n. Well, these are just Gaussian integers, and epsilon and epsilon double prime are units. So the way to do this is to use that the Gaussian integers are a factorial ring, or a unique factorization domain. They are a UFD. Therefore, we have it that gamma is going to be a product. So, okay, so as long as gamma is not a unit. So if gamma were a unit, then alpha and beta are units, and should be pretty easy to show. But and of course if gamma is 0, then it's completely trivial. So let's just assume it's not. So gamma is going to be a product over some I of pi ai. And therefore, gamma to the n is going to be a product over I of pi n ai. And therefore, epsilon times this product of pi n ai is going to be equal to alpha beta. Alright, and so now we can use this, and then we can just switch the primes around a little bit. So, you know, we can just mess around with the primes a little bit, and of course these are relatively prime, so none of these primes in this product right here are going to be the same, because that would be the greatest common divisor, not a unit. And so therefore, we have it that alpha, and remember, because of this n right here, it's going to be a power of n, so that's y. So alpha is going to be epsilon prime, some unit epsilon, times a product over k of pk nak, which equals, and actually I'm going to put this n on the outside of the product, and this is going to be epsilon prime times some zeta to the n, because this is a new unique factorization of some different number. And this right here, this k, doesn't have to be in the same order as that. You can rearrange the primes, it's fine. And we're going to have beta is equal to epsilon double prime product over some j, pj, aj to the n, which is equal to epsilon double prime beta to the n. Like so. And that's completes the proof. Right, you always have to be careful with units, right? So, we're allowed to do this because the product of two units is going to be another unit. So, epsilon prime times epsilon double prime, sorry, not beta to the n. Let's just have some mu to the n. So, epsilon double prime times epsilon prime is going to just give you epsilon. Alright, so the third one, let's do the third one. Just rub this out. It's actually the second one that took me the longest to do. I actually had to sleep on it, whereas the other ones I got it somewhat fast, quickly. Where did the black pen go? I lost my black pen, never mind. Alright, the third one is show that the integer solutions to x squared plus y squared equals z squared such that x, they're all positive, and they're relatively prime, are given by x equals u squared minus v squared, y equals 2uv, and then obviously that means z equals u squared plus v squared. Where u and v are integers, u is bigger than v is bigger than 0, and u and v are not odd. Alright, it's quite a long exercise. Let's do it then. Alright, so the way to do this is we use this exercise. Right here we have a product and we have a power of 2 on the right hand side. What is this? This right here, well, x squared plus y squared is equal to x plus iy times x minus iy. And these are co-prime in the Gaussian integers, which you can check if you like. These are co-prime. And then right here we have 1 times z squared. 1 is a unit. And so we have a product of co-prime things, and then a unit times z squared. Well, we just plug n in here, and then we're going to have this product here in the unit. So therefore we have x plus iy, for example, and just because the exercise gives it in terms of u and v, actually no, never mind. Alright, and this is equal to z squared. And therefore, x plus iy is equal to some unit epsilon times alpha squared, because they're power 2. Alright, and then we're just going to use this. Alright, now we're going to put alpha equal to u plus iv, because that's how these numbers are given here. So therefore we're going to get epsilon times u plus iv squared. In fact, I don't need these brackets here. Which equals epsilon times u squared plus 2 epsilon iuv plus, sorry, not plus, minus, because I squared is minus 1, minus epsilon v squared. Alright, so now all we're going to do is equate imaginary and real parts. So we're going to have x equals epsilon u squared minus epsilon v squared, which is equal to epsilon u squared minus v squared. And we're going to have y is equal to this part, the imaginary part right here. So we're going to have 2 epsilon uv. Now, right now we're really close, right? We just have epsilons inserted all over the place. So how do we show that epsilon is 1? Well, it's the only, well, if epsilon were negative 1, so we only have 4 choices to pick from. So if x, okay, let's just eliminate the odd ones. Plus or minus I. If epsilon were plus or minus I, then x and y would be imaginary, complex, which is clearly not an integer. So those two are out. And if epsilon were negative 1, well, right here, where is it? U is bigger than v, and x, y, and z are bigger than 0. So if this were negative, epsilon were negative, then we would have negative u squared plus v squared, and because v is less than u, then this would be a negative number, and also this would be a negative number. So that we can't have that either. So the only one which works is epsilon equals 1. So epsilon equals 1 must be. And so therefore we have that x equals u squared minus v squared, y equals 2uv, and therefore z equals, well, so let's just see, z squared equals x squared, which is u squared minus v squared squared, plus 2uv squared, so 2uv squared, which equals u to the power of 4 minus 2u to the squared v squared plus v to the power of 4, and then plus 4, so this is actually just going to be a plus just to save space, and this equals u squared plus v squared squared, which means that z equals u squared plus v squared as required. Alright. I'm sorry that the last bit became unreadable, but the important part is we get x and y, and then you can easily deduce z from there. Alright. So the fourth one is an interesting one. So for the fourth one, this is, I just used the proof that the complex numbers can't be ordered, which is quite a famous proof. And the same reasoning can be applied for the Gaussian integers. So exercise 4 says, prove that the Gaussian integers can't be ordered. Prove that the ring of Gaussian integers can't be ordered. How do we do this? Well, alright, so I is obviously not equal to 0. The imaginary unit is not equal to 0. Therefore, I is either bigger than, I is either bigger than 0 or I is less than 0. Assume I is bigger than 0. The same reasoning works if I is less than 0. That would mean that I squared negative 1 is bigger than 0. Alright, so right now we can still have a weird order, but multiply both sides by negative 1, and we also get that 1 is bigger than 0. And this is a contradiction, because if 1 were bigger than 0, then we could just add negative 1 to both sides and get that 0 is bigger than negative 1, which contradicts this. And the exact same reasoning can be used for I less than 0. So it's quite a neat proof. And it works, of course, exactly the same way for the complex numbers too. Alright, what's next? Show that the only units of the ring z square root negative d, which is equal to, as you might expect, the set of all x plus square root negative d y, such that x and y are integers, are plus or minus 1. So it's only units of plus or minus 1 for a non-square number d, I think. Yeah, for any integer bigger than 1. Any integer. Alright, so so the way to do this in commutative algebra usually is you give the ring a norm, and then you show that, and then the units, an element can only be a unit if and only if its norm is 1. So how should we define the norm? Well, the norm, we'll take in one of these numbers right here, and it will output a natural number, including 0. I'll just do union 0, so then, just in case you don't include 0 in your definition of natural numbers. Alright, which maps alpha, so an element of this, it maps it to, what should we do it as? X squared plus dy squared, because it will take in x plus square root negative dy, and it will map that to x plus square root negative dy times x minus square root of d negative dy. So you do the number itself times its conjugate, and this is equal to x squared plus dy squared. If you do the maths, if you do the FOIL. So let me just where alpha equals x squared. Alright, now alpha is a unit if and only if its norm equals 1. And this is very similar reasoning to the one I did for exercise 1. You just use the multiplicativity of the norm, which you can easily check to show that this is true. And therefore, alpha is a unit whenever, if and only if, x squared plus dy squared equals 1. Now actually, this is much more interesting when it's a minus sign there, in which case we'll be dealing with Pell's equation, and you'd have to use Dirichlet's unit theorem. I think that's the easiest way, to show that this actually has an infinite number of solutions. So if you just take away the negative d, I think you're going to have an infinite number of units, and you can use Dirichlet's unit theorem to prove that. So anyway, if alpha is a unit, then this right here must be 1. Now remember that d is positive, and so this can never be negative because x and y are integers. So this is only true whenever x squared equals 1 and dy squared equals 0. And this means that alpha equals plus or minus 1. Alright, anyway, that's it for today. I hope that you enjoyed the video, and yeah, well it's a good demonstration of, well, how to deal with such exercises, and this is just 5 more theorems, which is also very handy to know. Especially that one about the epsilon time, the second one I did basically. That one actually works for any unique factorization domain, and it's one of the reasons that it's such a nice property for a ring to have. Anyway, yeah, enough blabbing. That's it for today's video. I will do homotopical algebra next. Unfortunately, the lecture notes I'm reading for homotopical algebra don't actually have any exercise in them, so I can't do this for that series, but when I do an algebraic topology video next, I'll make sure I do the exercises, and then I'll do a video on those too. For example, whatever I do next. I might do Gaussian theory, I might just do more number theory, to be honest. Whatever, yeah. I'll see you next video, basically. Bye.